Hi everybody, this is Eric, and welcome back to Reading the Effin' Docs, where we learn Solidity together. And this is taking longer than I thought it would. We're still in the basic section here. And today, we're going over Solidity by example, and we're going to start with the voting contract, which is what we're going over today. I went ahead and opened this in Remix, and bear with me. One thing I like to do when I open up a new smart contract, especially when it's kind of complicated, is I like to minimize all the functions just to get a overview of what the contract does and what it's supposed to do bef before I dive into what each function does. Anyway, if you recall, a very sweeping generalization that I like to make about smart contracts is essentially what they have is some state and ways to manipulate that state. So what state do we have here? We have a public variable called chairperson, we have a mapping called voters, and we have an array called proposals. And let's talk about, and the rest of this are just functions that interact with them. We have, this is a voting contract. We have a constructor, we have a function to give the right to vote, to delegate your vote, a function to actually vote, a function to check to determine the winning proposal, and a function to get the name of the winner. Um, contract is called ballot. Let's talk about these structs real quick. Number one is we have a struct called voter. Struct, as you know, basically a user-defined data type. So, we're gonna have voters, people who vote on the various proposals. Each voter will have an associated weight, i.e., how much does your vote count for? A Boolean flag called voted. In other words, did you vote or not yet? A delegate, address of a delegate, optional. You can delegate your vote to another person or another contract, I suppose. And an actual vote, which is going to be uint, and this will be, what proposal do you want to vote for? Let's see. So now we have a proposal struct, and these are the things, proposals. You can propose that we mow the lawn of Central Park, or you can propose that we, add a fence around City Hall. I don't know, just some ideas. Each proposal is going to have associated name and a vote count. So I imagine the proposal with the highest vote count will win the votes, and there you have it. So these voters, they're going to be part of this mapping. So each address, so let's see. Okay, so yeah. So the mapping is called voters. So each person who wants to vote, they're going to have their address, and their address will be associated with this voter object. And you can call them as saying voters of, my address will have this information. And our proposals, it's going to be an array of these proposal objects. So that's the data structures. I wrote a quick sketch here. Not the best, example, but our proposals, we're going to have an array, and in our case, we're going to have two elements in the array. Just going to be a proposal called foo and a proposal called var, and they're each going to have a vote count initialized to 0. Now our voters, it's not an array, it's a mapping, so this is not the best representation. Oops. But we're going to have 4 voters, 1, 2, 3, and 4. Each one will have an associated voter object, a weight, voted flag, optional delegate, and what they actually vote for. So that's just how that all looks like. And let's go ahead and compile this and play around with it a little bit before we dive into each function there. So quick thing about this particular smart contract is the constructor takes in a bytes 32 array of proposal names, meaning we can't just type in strings of the proposals that we want. So we have to convert them into a bytes 32 representation. So I kind of wrote in here in this comment the function to do so. You can do this directly in the Remix console. That function is ethers.utils.format bytes 32 string. And we are going to enter in foo and bar. So foo gives us that is the bytes 32 representation of the string FOO. So we're going to enter in array, and it's going to have 2 bytes 32 strings. Let's type in foo. Oops. Let's copy that. Copy. Paste it in. And now let's do the same thing for bar. And this is for bar. Now, let's make sure that's formatted correctly. Okay, let's deploy this contract. And now we have our deployed contract. By the way, we're using, okay, the VM that comes with Remix. We're using that first account. This is going to be our 1 account. And this account here will be 2, 3, and 4. So quick note about the chairperson. You can see it becomes the address, initialized to the address that we just deployed with. Let's go ahead and go over this constructor. So essentially what we're doing is, and you might have seen the same pattern in other contracts, where in the constructor we take message.sender, which is the address of the entity that deployed the contract, and assigns that to an owner. And then you can use that owner for other functions, or you can restrict access to who can call the function, etc. But in our case, because it's a voting situation, we're calling it a chairperson, and we're initializing their right to vote to a weight of 1, so their vote counts as 1 vote. And then what we're doing is we're looping over this array we entered in. Now, in our case, we have 2 objects, foo and bar. And for each one of those, we are initializing a proposal struct and inserting it into this proposal array. So this proposal array at index 0 will be our foo proposal, and then index 1, we will have our bar proposal, and they will be initialized to have a vote count of 0, and the name will be foo and bar. So that's what that constructor does. So you can see here the go ahead and add it. So if I put proposal at the 5 index, okay, well, it gets nothing bad, it reverts. But if I look at the proposal at the 0 index, that's our bytes 32 representation of foo. And at the 1 index, that is the bytes 32 representation of bar. And our chairperson is, quote unquote, the owner of the contract. So that's how those work. And now what we're going to need to do is we have to give people the right to vote. Because right now, the chairperson can vote. But if I go to another contract and try to vote for foo, that transaction reverts. So as our chairperson, we are going to give people the right to vote. So let's go to address number 2 here. We will give them the right to vote. Let's grab the address of voter number 3. Let's give them the right to vote. Now let's grab the address of voter number 4. And let's give them the right to vote. Okay, great. So 4 people, and the chairperson was given the right to vote automatically at construction time. So we don't have to do this specifically for them. Now we can see if we take, I don't know, let's go back to voter, whoever this is. He's not 1, 2, 3, or 4. And look at his entry in the voters array. You can see it's empty. So he didn't get a weight of 1. Everything is initialized to the, the 0 value. But if we get voter number 2 and put their address in here, you can see they have a weight of 1, meaning they have the right to vote. And they were, in fact, added to our voters array. So winner's name and winning proposal, we don't check just yet. But now, one more thing before we start voting is I want voter number 2 to delegate his vote, or her vote, to voter number 3. So let's delegate to voter 3. So now if we grab voter number 3's address and look at their entry in the voters array again, we can see that they now have a weight of 2. So their vote counts twice as much as their original votes. And, we'll see how that factors in. So now let's go ahead and start voting. So our chairperson is going to vote for proposal 0. Now they voted. Voter number 2, let's see if we can vote. Look at that, the transaction reverts, and that's because we delegated our right to vote to voter number 3. Now, voter number 3, we'll let them vote, and they're gonna vote for, let's see, let's still have proposal 0. Now they voted, and voter number 4 is actually gonna vote for proposal number 1. They want Barr to win the election. So now everybody has voted. And let's go ahead and call winning proposal. This is going to calculate. And you can see our winning proposal is is the winner, and the winner name, if I have to take our word for it, that is the bytes 32 representation of foo. They were the proposal at the 0 index, and they should have 3 votes. So let's see here. Let's go to the proposals array. Let's go back to proposal number 0. So they have a vote count of 3. Now, if you remember, voter number 1, who's the chairperson, voted for this. Voter number 2 could not vote. That transaction reverted. But voter 3, because their vote was delegated to them by voter number 2, their vote counted as 2 votes. So that is why this proposal 0 has 3 votes, even though only 2 people voted for it. And proposal at the 1 index, which is Barr, that only has 1 vote. Now, so that's basically how this works. Now let's go through each function here. So we went over the structs, we went over the various states, we went over the construction. Now we had to go over give right to vote. This is only done by the chairperson. So you can see these require statements here. So if these require statements evaluate to false, this function will revert, and there will be no state changes, and nobody will be given the right to vote. So you have to be this first address in order to give the right to vote, because that is the chairperson. And likewise, the person you can see here, the person you're giving that right to, they must have not already voted. And their weight, they must have the right to vote. So they have the weight of 0. That means they don't have the right to vote, and you can't give them the right to vote. No, wait, I'm sorry, I take that back. They can't currently already have the right to vote. That's what I meant to say. And then by doing this, so if they don't already have the right to vote, then this line gets called on line 74, where you are officially giving their weight of 1. That's how that works. Now, delegate. This is an interesting one, and we'll see why in a second. And we have our checks here. Now, first, we're creating a variable called sender, which is basically the voter struct of the person calling this function, who wants to delegate their vote. So we have a few checks. Number 1, do they have the right to vote? Did they already vote? If they don't have the right to vote, or if they already voted, they have no business delegating their vote to anyone else. And they can't delegate to themselves, because that just doesn't make sense. So now is where it gets interesting. So a quick caveat to this function: consider a scenario where you want to give your vote to Bob, but then Bob delegates his vote right back to you, but you already go, and they have this circular loop there. And now in programming terms, we call that an infinite loop. And for solidity purposes, an infinite loop is pretty horrible. It's basically gonna cause your function to fail. So we want to avoid those situations. So that's what we're doing here. So essentially, we're going through the delegate chain, saying who delegated to who delegated to who. And if we find a loop, then this whole thing reverts and you can't delegate to anybody. So that's what this method's about. If you want to go through it, through the logic, it's a pretty good exercise. So now, once all these checks have completed, we go ahead and create a delegate voter. Or we grab the delegate voter that you want to vote to and put that, put that voter struct into a variable that we can just kind of easily look at. We make sure they have the right to vote, and then we go ahead and set your right to vote to true and set your delegate field to the to address. And then here, if that person already voted, we just increase the vote count of that proposal. If they have not voted, we increase the weight of their that they're allowed to for when they vote, and then it'll be used when they do finally decide to vote. Now, the vote function. What are we doing here? Okay, grab our sender. That's just a person who's calling this. Make sure they have the right to vote. Make sure they didn't already vote. Set their voted flag to true, and set their vote to the proposal that you choose. In our case, it'll be 0 or 1. And then we update the vote count of that proposal to be used later when we tally up the votes. Now, winning proposal. What are we doing here? We are essentially looping through all the proposals, counting up the vote count, and then the winning one gets declared. The one with the highest vote count gets declared the winner name, and this just returns the bytes 32 representation of who won. So after you call this winning proposal function, that's when you can call this winner name function, and it'll return a value. So that pretty much sums up how this works. I hope this was helpful. And one thing we can do to maybe improve this is make another function that says winner name, string, where we convert the bytes 32 representation of foo or bar back into a more readable string and return that. That could be, an interesting, I don't know, little exercise to do. So the authors of this documentation, after they, display the contract, they have a little, few questions for you. How can we approve this? So couple of things they talk about is, let's look at that first sentence. Currently, many transactions are needed to assign the rights to vote to all participants. How do we fix that issue? So what they're talking about is the chairperson. So suppose 5 people want to vote. In our case, we already had 4. Our chair, but what if there's more? What if there's 30 people wanting to vote? Our chairperson needs to call this give the right to vote function, 29 times. And because they themselves count as one. So they have to call this 29 times. And that can cause a lot of gas for, for the contract owner. One thing we can do is maybe have a register function where people can register themselves, and then they can add themselves to this voters mapping, and then let handle them. So, and they can handle, a small amount of gas by themselves versus the contract owner handling a lot of gas. That's one thing we can do. Just off the top of my head, they have another thing here. Moreover, if 2 or more proposals have the same number of votes, then winning proposal is not able to register a tie. Okay, how do we deal with a tie? One option, probably not the best one, but the first thing that comes to my head, one thing we can do is that as we call this winning proposal function, instead of keeping track of the highest vote count, maybe we keep track of the highest 2 vote counts. And, if they're equal, then we can say, hey, there's a tie, or have some return value that signals there's a tie. Maybe we return a tuple instead of, what are we returning here? A uint instead of just a uint. That's one option, but that doesn't account for the case of a 3-way tie. So there's probably other things you can do, probably some cool other data structure that just escapes my mind right now. that we can be using, but that's, just off the top of my head, something to think about. So that's pretty much it. We went over the smart contract, what it does. We interacted with it. We went over some possible ways to improve it. And let's see, we got a few more of these before we're out of the basic section, but either way, I hope this was helpful. My name is Eric, and I work for CryptoPunks. Take care.